Hi all, welcome back to 3 Deviations. In this video we want to finish off our analytical techniques of integration with inverse function integration. Now this is kind of an extension of integration by parts, but it can be helpful sometimes when your inverse function might be easier to integrate as opposed to your normal function. So we'll try that today, and this is the last technique of integration, the last analytical technique that we're going to be doing. Then we're going to be moving on to Simpson's rule and improper integrals, and we're going to be done with Unit 6. All right, so let's get started. So the formula is pretty simple. So it says that the integral of the inverse, f inverse of x with respect to x, is equal to x times f inverse of x minus capital F of the inverse of f of x, so that's a composition of functions there, plus c. So this is, you can kind of see how this is an expression of integration by parts a little bit, because you can see the x term here. You can see kind of how that might not be related to x anymore, so you're kind of reducing, right? And when we define f, so f is equal or defined as the integral of little f of x dx. So that's a little important tidbit there. So now what we can do is we can do a couple of examples. Yeah, so this is going to be a rehashing of some of the examples that we've already done, but we'll have a look at it. So here's an example, and we're going to go back to a little bit of trig here. So I would like us to integrate the inverse sine function. So to integrate the inverse sine function, we could use integration by parts and just add the x, but we're not going to do that. We're going to make life a little bit more interesting by doing this formula here. So sine inverse of x, so sine minus 1 of x, then we can go to our inverse function of that, which is just sine of x, right? So our inverse function is sine inverse of x. Then our uninversed function is sine of x. And capital F of x is the integral of sine of x, which is negative cosine of x. So now we're going to apply the formula. So it says x times the inverse function, so that's x times sine inverse of x, minus large F of f inverse, so that's plus cosine of sine inverse of x plus c. Okay, so we want to simplify this. So we're going to go back to our triangle here. We're going to make a triangle. So we're going to set sine inverse of x equal to theta. So that means that x here is our opposite side, because if you remember, SOHCAHTOA. So there's our theta, and there is our opposite side. Then we've also got our hypotenuse, which is 1, because x over 1 is x, so we get sine inverse of x equals theta, right? So that means that this side, by the Pythagorean theorem, is the square root of 1 minus x squared, right? So now we need to find cosine of theta. So cosine of theta is the adjacent over the hypotenuse. So that's just going to be 1 minus x squared. So now we can rewrite this as x sine inverse of x plus, so the cosine of theta is just square root of 1 minus x squared. And that is the same thing that you would find plus c when you do an integration by parts as well. So that's pretty helpful, I think. All right. So now let's move on to another one. This is going to be something that we've already derived. We've given it its own video. So we want to integrate the natural log function. So if you remember, the natural log function is the inverse of the natural exponential function. So we have e to the x, and then we have the natural log of x. Sorry, this notation probably isn't right, the double-sided arrow, but that's what I wrote. Oops. All right, so we can find our f inverse of x as being equal to logarithm of x. So then f of x is e to the x, and then capital F of x is the integral of e to the x, which is e to the x. So now we get x ln x minus e to the ln x. Now e to the ln x, since these are inverse functions, these are going to cancel out, so you just get x ln x minus x plus c. All right, so that's all I got for inverse integration. May have skipped this video, but yeah, it's nothing super official, but it's a nice tool to have in your integration arsenal. So we've covered integration by parts, we have covered trigonometric reduction, we have covered trigonometric integrals, trigonometric substitution, Weierstrass substitution, partial fractions, and now inverse integration. So those are our techniques of integration that we wanted to cover, and now we're going to move into a numerical technique called Simpson's rule, and then we're going to talk about improper integrals, which is when we deal with integrals around asymptotes. And these are both definite integrals. We haven't been doing many definite integrals, so we're going to look at that. All right, we'll see you in the next one. Bye.